If you rent a house and the landlord calls you up to say, hey, just a heads up, in exactly 1 year, I am bulldozing this place to the ground, you don't start arguing over what color to repaint the kitchen.
Right, you pack your bags.
Exactly. You pack up, you immediately start figuring out your exit strategy.
It's a really compelling analogy. I mean, it makes sense, but it kind of misses a crucial variable in our actual reality. Because what if you literally cannot leave the house?
Like you're trapped inside.
Right. What if the doors are locked? You don't know how to build a car to drive away, and the house itself has, like, a faulty furnace that's actively trying to suffocate you long before the bulldozer even arrives.
Wow. Okay, that is a much, much more stressful living situation.
Yeah, it's bleak.
Well, welcome to this deep dive. If you're listening right now, you are probably someone who wants to understand the grand sweeping narrative of our future, but, without getting bogged down in impenetrable academic jargon. And today, we have an incredible stack of sources for you. We are looking at deep time documentaries, astrophysics thought experiments, and some just incredibly audacious real-world engineering proposals.
Yeah, the overarching mission here is to really explore the ultimate survival guide for humanity.
The survival guide, I like that.
Because what the sources reveal is this fascinating paradox. I mean, technology is constantly framed in our daily news cycle as the primary existential risk to our survival. Like, it's the thing that's going to end us.
Oh, absolutely. It's always doom and gloom.
Right. But it is also, unequivocally, our only viable ticket preventing human extinction and outliving Earth's natural expiration date.
And just to put our current technological status into perspective for you guys listening, there's this mind-bending statistic in these sources. So astrophysicists use something called the Kardashev scale to measure a civilization's cosmic advancement. And it's based entirely on its energy consumption.
Right. It's all about energy.
Right. So a Type 1 civilization harnesses all the available energy of its home planet. Type 2 harnesses the entire output of its star. And Type 3, its entire galaxy. So guess where humanity sits right now?
I mean, spoiler alert, we aren't even at a 1 yet.
Nope, not even close.
Right.
We are currently sitting at a mere 0.72 or, well, maybe 0.73 on a good day.
Which tells us a lot about our vulnerability, Being at a 0.72 means we are still entirely at the mercy of our planet's natural cycles. The clock is absolutely ticking.
Because we can't leave the house yet.
Exactly. Before we can even think about conquering the stars and reaching Type 2 or 3, we have to survive our own rebellious planet. Earth systems, from the lithosphere shifting beneath our feet to the atmosphere above us, they are incredibly volatile.
Yeah, the planet isn't exactly playing nice.
No, it's not. So to bridge that gap to a Type 1 civilization, we are forced into a position where we have to fight back using some pretty extreme geoengineering.
Okay, so let's start with the ground beneath us then, specifically volcanoes, because the sources bring up supervolcanoes like Mount Toba in Indonesia. An eruption on that scale today it could instantly wipe out 1 billion lives.
Easily. And plunge the rest of us into a volcanic winter.
Right. But there is a proposal from a NASA engineer in these sources that just completely flips the script on this threat.
Yeah, and what's fascinating here is the sheer audacity of the mechanism. Because you don't just try to plug a volcano, right? You bleed it.
Wait, bleed it, like medically?
Sort of. The proposal outlines drilling a series of boreholes, like several kilometers deep, positioned right outside the perimeter of a supervolcano's magma chamber. And then you pump highly pressurized cold water down into the surrounding rock.
Okay, let's unpack this for a second, because you're essentially trying to use a planet-killing volcano as a giant subterranean boiler.
Precisely. It's just basic thermodynamics, but applied on a planetary scale. So the water descends, it absorbs the massive thermal energy radiating from the magma chamber, becomes superheated, and then
it shoots back up.
Yeah, it's pumped back to the surface to drive steam turbines. So you are extracting the heat to generate this endless supply of clean geothermal energy.
Wow.
But the primary goal isn't just keeping the lights on, It's planetary defense. Because by continually bleeding off that heat over tens of thousands of years, you gradually cool the magma chamber itself.
So it can't erupt.
Right. You literally turn the magma into solid rock until the thermal pressure required for a catastrophic eruption is completely neutralized.
That is brilliant. You disarm the geological bomb and you power your civilization with the wiring from the bomb itself.
Exactly. It's a 2-for-1.
But the ground isn't our only problem, is it? The atmosphere is heating up and it's doing it much faster than a supervolcano builds pressure.
Very true.
So in 1991, Mount Pinatubo erupted and ejected, what, 20 million tons of sulfur dioxide into the stratosphere, and it reflected so much sunlight that global temperatures actually dropped by half a degree Celsius for nearly 2 years.
And that cooling effect wasn't just some historical anomaly to read about.
Right.
I mean, it gave climate scientists a literal blueprint for our next defense mechanism, which is known as stratospheric aerosol injection.
Right. So how does that actually work in practice? Because I've heard it described as, putting sunscreen on the earth, but that feels a little, I don't know, overly simplistic.
Oh, it is definitely simplistic.
Yeah.
A better way to visualize it is to imagine shattering millions of microscopic mirrors up in the upper atmosphere.
Okay, mirrors. I can picture that.
Yeah. So when sulfur dioxide reaches the stratosphere, it reacts with water vapor to form these tiny, highly reflective sulfate aerosols. And these act like tiny prisms, catching incoming solar radiation, specifically the infrared heat, and bouncing it straight back into the void of space,
Before it can even reach us down here.
right before it ever reaches the troposphere where we live. And the chemistry is just astonishingly potent. I mean, a single ounce of sulfur dioxide dispersed up there can offset the warming effects of several tons of carbon dioxide for an entire year.
An ounce offsets tons. That's incredible. But spraying reflective chemicals into the sky isn't the only solar shield idea in our stack of sources today. There's a team at MIT that has proposed building an actual physical sun shield in space.
Yes, the space bubbles.
Yeah. They want to place it at a Lagrange point. And if you're listening and wondering what a Lagrange point is, it's essentially a gravitational parking spot. It's where the pull of the Earth and the pull of the sun perfectly balance out so an object just hovers there in space.
Right, specifically Lagrange point 1 for this project. The MIT concept involves deploying this massive array of inflatable silicon bubbles.
Bubbles in space.
Yeah, but to block just 1.8% of the sun's light, which is the calculated amount they say is needed to bring global temperatures back to pre-industrial levels, this bubble shield would have to be roughly the size of Brazil.
Just the size of Brazil, just floating between us and the sun.
It's massive engineering.
It is, and yet the engineering gets even more radical when we look at how to pull the carbon that is already trapping heat out of the biosphere. The sources detail researchers designing these things called mechanical trees. But I have to ask, how does a machine replicate, billions of years of photosynthetic evolution?
Well, it doesn't use photosynthesis at all. It uses sheer chemical binding. So these mechanical trees are essentially massive vertical columns of specialized chemical sorbents.
Like a sponge?
Kind of, yeah. Think of them as giant artificial lungs. When the wind blows air through the columns, the carbon dioxide chemically binds to the dry sorbent material. And then once the column is saturated, it drops down into a sealed drum, gets hit with water or steam, and that humidity swing forces the material to release the pure CO2.
Oh, so you trap it, release it in a controlled way, and then what?
Then it's captured and sequestered deep underground. And the wild part is, a single one of these structures can pull carbon out of the air 1,000 times faster than a living tree.
1,000 times faster. So you could build like a forest of 100 million of these metallic columns and theoretically offset all of humanity's current carbon emissions.
Theoretically, yes. Though you still need a place to put all that captured carbon once you have it.
Which brings me to my absolute favorite, and by favorite I mean most terrifying concept in these sources. It's an idea for the oceans. I saw the phrase Kerguelen Plateau in the notes right next to the words nuclear detonation. Please tell me I misread that.
You definitely didn't misread it. This is the absolute extreme of geoengineering. So the Kerguelen Plateau is this massive underwater microcontinent in the Southern Ocean. And the proposal suggests detonating a nuclear
A
weapon.
nuke in the ocean.
Yes, a nuke potentially 1,000 times more powerful than the Tsar Bomba, which is the largest nuke ever created.
Yeah.
You detonate it about 5 kilometers deep, right inside the seabed rock.
Okay, wait. How does detonating a gigaton nuclear bomb on the seafloor help the climate? Because that sounds like the literal opposite of a solution. It sounds like the end of the world.
I know, it sounds insane, but the mechanism is actually based on the natural carbon cycle.
Huh.
So the deep sea pressure down there is so immense that it completely contains the radioactive fallout deep underground. It doesn't reach the surface.
Okay, sure, but what about the explosion itself?
Well, the sheer kinetic shock wave of the blast shatters and pulverizes thousands of cubic kilometers of barren basalt rock. And by turning that solid bedrock into highly fractured rubble, you exponentially increase its surface area.
Right, because it's all broken up into tiny pieces now.
Exactly. And when the carbon-heavy ocean water interacts with all those freshly exposed silicates, it triggers a massive chemical weathering process. The rock basically drinks the carbon. It permanently locks 30 years' worth of global CO2 emissions into solid mineral form almost overnight.
Okay, I have to pause here because, I mean, let's unpack this. Detonating subterranean nukes to shatter the ocean floor. Building a space shield the size of South America. This sounds exactly like a James Bond villain's master plan.
It really does.
If you're listening to this, you're probably thinking, aren't the consequences of hacking the planet just as terrifying as the climate problems they're supposed to solve? I mean, what if we mess it up?
It's an incredibly important point, and to be fair, the sources don't shy away from the severe, unpredictable risks. Hacking the planet is entirely fraught with danger.
Right.
For instance, if you deploy stratospheric aerosol injection, the sunscreen, you aren't just lowering the temperature. You are fundamentally altering the thermal dynamics of the atmosphere.
Which changes the weather.
Radically. That could shift global monsoon patterns, potentially inducing massive localized droughts that threaten the food supply for billions of people in places like Southeast Asia or Africa.
Which instantly creates a massive geopolitical nightmare.
Precisely. Because if one nation, acting in its own self-interest, decides to deploy a global cooling mechanism, but it accidentally causes a famine in a neighboring hemisphere, you have the immediate recipe for a catastrophic armed conflict over who controls the global thermostat.
So we're damned if we do, damned if we don't.
Well, not exactly, because this raises an important question about timelines. Doing nothing guarantees our extinction.
That's true.
The supervolcano will eventually erupt. The climate will eventually reach a breaking point. We are rapidly approaching a threshold where we have absolutely no choice but to actively manage the lithosphere and the atmosphere just to survive. We basically have to become the architects of our own planet.
But pulling off these godlike planetary hacks, like coordinating global weather patterns, modeling the exact dispersion of aerosols, managing subterranean thermodynamics, and doing all of that without accidentally destroying ourselves in the process, that requires a level of computational power and predictive modeling that is just far beyond human brain capacity.
It's impossible for us to do alone.
Yeah, exactly. Which brings us to our greatest tool and, ironically, our most imminent existential threat. Artificial intelligence.
Right. And to understand the real stakes of AI here, we need to look at how the sources frame the Fermi paradox. So the universe is incredibly ancient. It contains trillions of habitable planets. So where is everybody?
Why haven't we heard from anyone?
Right. Why haven't we detected a single radio signal or megastructure from an advanced alien civilization?
Which naturally leads to the Great Filter theory.
Yes. The Great Filter theory posits that there are universal evolutionary bottlenecks that intelligent species simply fail to pass. They reach a certain level of technological maturity, perhaps just before hitting type 1 on the Kardashev scale, and then they inevitably wipe themselves out.
And looking at our current trajectory, I mean, AI might just be our great filter. Because the doom scenarios detailed in the sources are chilling. And we aren't just talking about a Hollywood scenario with Arnold Schwarzenegger Terminators running around.
No, it's much more subtle than that.
We're talking about incredibly complex, misaligned systems. Like a rogue AI tasked with environmental optimization might just objectively decide that humans are the primary inefficiency. Or a bot could engineer and release a biological pathogen that our immune systems have never seen simply because it was asked to solve a population density equation.
Or consider a much quieter, slower filter, something like societal atrophy.
Oh, like Wall-E.
Sort of. Humans could become so entirely dependent on AI infrastructure to manage our agriculture, our power grids, and our medicine that we completely lose the underlying knowledge of how those systems actually work.
We forget how to run the world.
Exactly. If a solar flare or cascading glitch knocks out the servers, we wouldn't even know how to begin rebuilding. We would just quietly fade away, having completely outsourced our own survival.
It's so deeply concerning that figures like Elon Musk and Geoffrey Hinton, who is literally one of the godfathers of AI, they signed an open letter asking for a 6-month pause on advanced AI training just to figure out what we're actually building.
Yeah, we're moving so fast.
So what does this all mean for us? It feels like humanity is trying to build an interstellar rocket ship while simultaneously wiring a bomb, and we have no idea which wire we're going to cross first.
That is exactly the tension of this decade. But the paradox revealed in the sources is that the rocket ship actually needs the bomb's wiring to fly.
Like, really?
Yeah. AI is exactly how we navigate around the Great Filter. For instance, the sources highlight how Google's DeepMind recently mapped the structure of millions of new inorganic crystals. That is the equivalent of 800 years of human material science knowledge, generated almost instantly.
Okay, but Why do crystals matter for our survival? I mean, that sounds cool, but
Because those new material structures are the exact data we need to accelerate commercial nuclear fusion, to build vastly more efficient solar panels, and to create the high-stress materials required for things like space elevators. We literally cannot invent the future fast enough using just the human scientific method.
that makes a lot of sense. And we even need AI just to keep our current orbit safe. There's this terrifying concept in the sources called the Kessler syndrome. Have you heard of this?
Oh yes, it's a nightmare scenario.
It's a potential chain reaction where a piece of space debris hits a satellite and completely shatters it. And that creates a cloud of shrapnel traveling at like 17,000 miles per hour, which destroys more satellites, creating more debris, until the Earth is entirely trapped in an impenetrable, swirling cage of deadly metal. We'd just be trapped on Earth forever.
And how do we stop it? By deploying AI-guided laser systems on satellites. Because these systems can track millions of pieces of microdebris in real time, predict their orbital trajectories, and fire short laser pulses to vaporize or slightly nudge the debris out of a collision course. Humans physically cannot calculate or pull the trigger fast enough to manage an environment like that.
So the key to our survival isn't avoiding AI altogether. It's about the kind of AI we build.
Exactly. The pattern in the research strongly suggests we must focus on building narrow, tool-like AIs. We need an intelligence that is exceptionally smart at predicting protein folding or targeting space lasers, but operates within strict, mathematically unbreakable guardrails.
Right, narrow focus.
What we must actively avoid is wide agentic AI. An intelligence that is completely autonomous, sets its own goals, and operates entirely without human oversight.
So our foresight right now, in this exact decade, regarding how we regulate and restrict machine learning, that is the actual test. It's the test of whether we possess the societal resilience to survive and finally graduate to a Type 1 civilization on the Kardashev scale.
But if we pass that test, like if we successfully use AI to leap over the Great Filter, harness all of Earth's geothermal and wind energy, stop the supervolcanoes, and control our climate, we immediately run into a completely new existential wall.
Because success comes with a massive price tag. I mean, if we hit Type 1 status, our energy consumption will have skyrocketed exponentially. The Earth simply won't be big enough to handle it. And if you're listening and wondering, well, why not just use perfectly clean energy? It turns out it's not a pollution problem. It's a fundamental thermodynamics problem.
That's right. It is the waste heat problem. The first law of thermodynamics tells us energy cannot be destroyed. It only changes form. So no matter how clean your energy source is, even if we master perfect, zero-emission nuclear fusion, using hundreds of trillions of watt-hours of energy on the surface of the Earth, inevitably generates heat as a byproduct.
Oh, wow. I didn't even think of that.
Yeah. If our energy consumption continues to grow at its historical rate to sustain a Type 1 civilization, the accumulated waste heat will eventually raise the global temperature by over 20 degrees Celsius.
We would literally boil our own biosphere just by keeping the servers running and the lights on.
Which means the only way to save the Earth is to leave it.
Right.
We have to move our heavy industry, our server farms, and our massive power generation into the cold vacuum of space, where the immense waste heat can radiate away harmlessly into the cosmos. And that migration, that's what marks the transition toward becoming a Type 2 civilization.
And remind us of the scale here, because a Type 2 civilization controls the entire energy output of a star. In our case, the sun. We are talking about capturing an unfathomable 400 septillion watts of continuous power.
It's a number we can't even really comprehend, but to capture even a fraction of that, the physicist Freeman Dyson theorized back in 1960 that we would need to build what is now called a Dyson sphere. Or actually, more realistically from an engineering standpoint, a Dyson swarm. Yeah, millions, maybe billions of massive, ultra-thin, solar-collecting satellites orbiting the sun in a dense overlapping formation.
But the sheer scale of that engineering is almost incomprehensible. I mean, if we're building billions of massive solar sails and energy transmitters, where do we even get the raw materials? We surely don't have enough steel and silicon on Earth to do that.
We definitely don't. And even if we did, stripping our own biosphere to build a star net completely defeats the purpose of saving the Earth in the first place.
True. So where does it come from?
If we connect this to the bigger picture, a Type 2 civilization has to look at its solar system not as a series of worlds, but as a quarry of raw materials. To build a Dyson swarm, humanity would have to unleash a fleet of automated, self-replicating mining drones to physically dismantle the entire planet of Mercury.
Okay, disassemble an entire planet, just layer by layer down to the core. But why Mercury specifically?
Well, three reasons. First, it has no atmosphere to slow down the launch of materials into orbit. It's much easier to get things off the surface. Second, it is incredibly close to the sun, making it the perfect logistical staging ground for launching satellites into solar orbit.
Location, location, location.
Exactly. But most importantly, Mercury is incredibly rich in iron and oxygen. And those are the exact chemical raw materials you need to smelt highly reflective solar collectors and build the immense infrastructure required to beam that microwave energy back to orbital space habitats.
Here's where it gets really interesting to me because we are talking about literally strip mining a celestial body out of existence. It is the ultimate cosmic home renovation project.
It really is.
Yeah.
And once you have the energy of an entire star at your disposal, you don't just sit there. You can initiate projects on a galactic scale.
Yeah.
A Type 2 civilization could actually build stellar engines.
I saw this in the sources, moving the solar system like a giant spaceship. But how does that even work physically? I mean, you can't just put a steering wheel on a star.
No, you don't need a steering wheel. You need asymmetric radiation pressure. So a stellar engine, like a Shkadov thruster, is essentially an unimaginably massive, curved mirror positioned millions of miles away from the sun.
A mirror. Again with the mirror.
Yeah, doesn't orbit, it just hovers there, balanced perfectly by the solar wind.
Mhm.
And by reflecting a massive portion of the sun's own radiation back at it, you create a slight imbalance in the star's thrust.
Wow.
Over millions of years, that gentle, continuous push physically moves the star through the galaxy, and it drags all the planets along with it through gravitational tethering.
So if our AI systems detect that our solar system is, say, drifting too close to a neighboring star that's about to go supernova and obliterate us with gamma rays, we steer our sun out of the way.
Exactly. We just move the whole neighborhood. And that mastery of stellar movement is just the stepping stone to becoming a Type 3 civilization, one which controls the energy of an entire galaxy. That means harvesting the power of the Milky Way's 100 billion stars.
But it's not just the stars they're harvesting, right? Sources suggest a Type 3 civilization would aim for the monsters in the dark.
Yes, these supermassive black holes, specifically Sagittarius A star, which is the black hole at the center of our galaxy. The physics actually allow for an advanced civilization to drop massive magnetic harnesses into the accretion disk, the swirling ring of superheated matter orbiting the black hole.
Wait, I thought nothing escapes a black hole, so how do you extract energy from it?
Right, so you aren't extracting energy from inside the event horizon, you're extracting it from the rotation of space-time itself just outside of it.
Oh, outside. Okay.
Yeah. As a black hole spins, it literally drags the fabric of space-time along with it, creating a region called the ergosphere. By firing mass into this region and using precisely aligned magnetic fields as transmission lines, a Type 3 civilization can siphon off that rotational kinetic energy. It is arguably the most efficient and powerful energy source in the known universe.
Man, if you're listening to this, take a second to just wrap your head around that journey. I mean, we started this deep dive talking about pumping cold water into magma chambers just to stop supervolcanoes. Then we navigated the razor-thin wire of AI guardrails so we don't accidentally delete ourselves. And we end up strip mining Mercury, sailing our sun across the Milky Way, and feeding off the rotational spin of supermassive black holes.
It is an incredible trajectory, and it all connects back to why this matters to you listening right now.
Right.
The incremental technological steps happening in labs today, like the AI breakthroughs in mapping crystal structures, the slow but steady increases in thermal efficiency, the intense global debate over how to regulate autonomous machine learning. These are not just isolated news stories to scroll past.
No, they're the foundation.
They are the exact required foundational steps to save us from extinction tomorrow. We are laying the microscopic bricks for a Dyson swarm today.
We really are. But before we wrap up, I want to leave you with a final, slightly mind-bending concept from the sources that really puts all of this cosmic ambition into perspective.
Let's hear it.
So, if we actually pull this off, if we use technology to survive the Great Filter, if we spread across trillions of planets to manage our waste heat, if we genetically alter our bodies to handle low gravity, and if we merge our biology with our machines to survive the harsh radiation of deep space, we are not going to remain a single monolithic species.
Right. How could we?
Exactly. Across the vast isolating distances of space and deep time, pockets of humanity will adapt to their incredibly specific cosmic environments. We will eventually splinter into millions of entirely different, highly specialized species.
Just a magnificent galactic branching of the evolutionary tree.
Right. So the ultimate irony of our survival guide. By the time our descendants completely conquer extinction, harness black holes, and master the energy of the universe, they won't even be human anymore. The entities that inherit the stars will look back at us sitting here worrying about AI and climate change the exact same way we look back at the earliest single-celled organisms floating blindly in the ocean.
We are just the very beginning of the story.
So when that cosmic landlord finally shows up with the bulldozer for Earth a few billion years from now, the beings that used to be us will have long since moved out, built an indestructible mansion across the galaxy, and entirely forgotten what a kitchen even was. Thanks for taking this deep dive with us. Keep your eyes on the stars, and we'll catch you next time.